So today we're going to learn a little bit about the sampling distribution for a sample proportion. So if you remember what we had talked about last week when we introduced sampling distributions, is that when we look at a sampling distribution, it is the collection of all sample statistics So in this case, because it's proportions, it would be the collection of all possible p hat values that are taken when we have repeated samples of the same size. So yesterday we looked at binomial distributions and how we could normally approximate them under some circumstances. And the sampling distribution for a sample proportion is just kind of an extension of that binomial distribution case, where if certain conditions are met, we can go ahead and estimate where the center of that sampling distribution is. So figuring out where all of our p hat values collectively will tend to fall with a certain amount of variability. So we'll calculate that standard deviation. So here is an example. We want to try and decide how well our statistic p hat is doing at estimating some unknown parameter p. And so in this case, we're going to consider Reese's Pieces candies. We have two different cases that we're going to consider. We're going to consider the case where the population proportion is 45% orange. And then separately, we're going to consider the scenario where it's 15% orange. So over here on the left, this is the case where the population is 45% orange. And this dot plot is a simulated sampling distribution where we're taking repeated samples of size 25 from this population that's 45% orange, and we're calculating the sample proportion of orange candies. So for example, there were several values where 60% of the sample was orange. You've got some values here where 40% of the sample was orange. When we collectively put all of those proportions together, we get this simulated sampling distribution, which is centered pretty close to 45%. And then we have the standard deviation of about 10%. And we'll talk about how that's calculated in just a couple minutes. In this case, with the 45% orange, this distribution here is pretty symmetric, single peaked, so we can say that it's roughly normally distributed. If we now consider a second scenario where we are still looking at 45% orange, but this time we are taking samples of size 50. We can see that it's still centered pretty close to 45%, but our standard deviation has decreased to about 7%. Still roughly symmetric here and single peaked in terms of that sampling distribution. So we can see that the mean is pretty close in both of these. Standard deviation is lower with the larger sample size. We see a little more normality over here in this case than we see over here. Then if we consider the case where we have 15% orange, over here on the left, we're taking samples of size 25. We can see the mean of that sampling distribution is about 15%. Standard deviation here is about 7%. This is going to be kind of slightly skewed to the right. If we were to draw a bell curve over top of it, we can see a slightly longer stretch on the right-hand side than on the left. Over here, we're still looking at a simulated sampling distribution that's 15% orange candies in the population. And in this case, hang on, it didn't pop up yet. There we go. We are centered again around 15%, But when we take that larger sample size, that standard deviation of about 7% from 25 for a sample goes down to about 5%. So the sample size is definitely playing a role in our standard deviation. We also see that this sampling distribution is a little bit more normal than this one was over here on the left with the smaller sample size. So here yesterday, so we don't really say in chapter 6, but we learned that the mean and standard deviation for a binomial distribution has a mean n times p. Standard deviation was square root of n times p times 1 minus p. Our p hat value is just x, which is our binomial random variable, divided by n, which we can just kind of expand this here into 1 over n times x. So we can use this fact to calculate a mean and standard deviation for proportions just by taking our binomial formulas and multiplying by that scale factor of 1 over n. So if we take here the 1 over n times that binomial mean here of n times p, the 1 over n and the n are going to cancel each other out. That simplifies just to p. So the center of our sampling distribution for proportions we denote as mu sub p hat. That's just equal to p. And then for our standard deviation, we can do the same thing. We can take our standard deviation from binomial and multiply by that scale factor of 1 over n. And here we just want to clean this up a little bit. So we can get the 1 over n underneath the radical by making it a 1 over n squared. So here's your binomial standard deviation up top, underneath the radical, n squared on the bottom to get this 1 over n underneath. And then we can simplify a factor of n from both the numerator and denominator. So the standard deviation of the sampling distribution for proportions is going to be the square root of p times 1 minus p over n. So this ultimately means that we're using p hat to estimate p. And then as our sample size increases, since it's in the denominator over here, it's going to give us a smaller amount of variability. So that will always be the case. As we bump up sample size, variability will decrease. Now, you're not going to have to go ahead and derive these formulas and go from binomial to these sampling distribution formulas. This is really just why these formulas are what they are. So you'll just have to be able to say that the center of the sampling distribution for proportions is equal to p, and the standard deviation of that sampling distribution is equal to the square root of p times 1 minus p over n. Or again, your book uses q instead of 1 minus p, so you can say square root of p times q over n, where q is that probability of failure. So here is an example. I'll give you guys a minute to read this one. So here, we're going to solve this problem very similarly to what we did with the binomial distributions. We're going to use z-scores. Our rule for being able to use z-scores with our sampling distribution for proportions is the same as what we saw with the binomial distribution. So as long as n times p and n times 1 minus p are both at least 10, then that sampling distribution is going to be approximately normal, which again means we can use z-scores. So just like what we had with the binomial distribution, even if n times p and n times 1 minus p weren't at least 10, we could still use these formulas for mean and standard deviation. It just wouldn't be safe to plug them into the z-score formula and then go to Staplet or Table A to find a corresponding probability. So here, in this case, we have 1,500 first-year college students, and it tells us that 35% attend college within 50 miles of home. So we want to figure out that if we take this sample of size 1,500, what's the likelihood that our sample is going to be within 2 percentage points of this true probability? So just to restate that to make it a little bit easier to understand is that we're really looking for what's the chances that our sample proportion is going to be within 2% of 35, so really between 33% and 37%. So because we have a sample of size 1500 and we have a proportion of 35% that are attending college within 35 miles of, or within 50 miles of home, we can find our mean and standard deviation for that sampling distribution. The mean is just going to be that population proportion of 35%. Standard deviation, we have that 35% times 65%, because this is just 1 minus 0.35, over the sample size, and then we take the square root. So what this is ultimately telling us is that our sampling distribution is centered around 35%, and then roughly counting up by values of about 1.2% for our standard deviation. And this sampling distribution is approximately normal because n times p, that's 1500 times 0.35, and n times 1 minus p, 1500 times 0.65, both of these numbers are above 10. So because of that, we can go ahead and use z-scores and then either Table A or Staplet to find the probability. So for the z-score, this is a between case. We're between 33 and 37%. So you're going to have to find two z-scores. You'll find one z-score for 33%, one z-score for 37%. And then we're going to look at the area in between those two values. So here, if I get rid of those red marks, this is just showing it on a standard curve that's now centered at 0. But before we even look at that, you have your z-score calculations here. So this first z-score calculation is for the 33%, so 0.33 minus this mean of 0.35 over this standard deviation of 0.123. That's the negative 1.63. And then the second z-score is for the 37%, so 0.37 minus the mean over the standard deviation for positive 1.63. If you're using Table A, if I look up 1.6, where it intersects with 0.03, that area to the left is going to be 0.9484. But that is everything to the left. And I only want this green shaded region here that I'm now overlapping in red between the two. So again, if I'm using the table, I have to then get rid of this area to the left of negative 1.63. So then I also go to the table, negative 1.6, where it intersects with 0.03. That is the 0.0516. And so this area in between is going to be roughly 89%. It's the difference between the 94.84% and 5.16%. Subtracting these two values will give that probability here. If you're using Staplet, because you've standardized, you found your z-scores, you type in your mean of 0, standard deviation of 1, and then when you hit draw curve or show curve, underneath it you can then select the option for calculating the area, and you would put in a lower bound of negative 1.63 and an upper bound of positive 1.63. So if we take a sample of size 1500, there is about an 89 to 90% chance that those students would be within 35 or 2% of the 35%. So I can get rid of this over top of the calculation here, or over top of the conclusion so that you can see. And again, that's due to sampling variability. We don't expect our sample to match the population value of 35% exactly. So we're saying that there's about a 90% chance that our sample is going to be within 2% of that value. So here's another example that we're going to take a look at. This time we have a sample of, it's covered on my screen. 1,785 adults who went to church last week, and the newspaper claims that 40% of all adults went to church last week. So we want to just suppose that this claim is true. We're going to use that to find the mean and standard deviation for that sampling distribution. So the mean of the sampling distribution is just that 40% about the population. Standard deviation is the square root of p times 1 minus p over n. So it's going to be a 0.4 times 1 minus p, which will be 0.6, over n, which is 1,785. So if I type that into my calculator here real quick, oops. I get 0.0116. One thing that I do want to mention here with these calculations, this value under the radical does get really small with a lot of these calculations. So when I typed this into my calculator and I did 0.4 times 0.6 divided by 1,785, my calculator gave me 1.34 times 10 to the negative 4. So just be really careful with those scientific notation values. Either kind of do everything all in one shot, or just make sure you're always looking for that scientific notation. Because if I were to take the square root of 1.34 instead, that would give me a very different and incorrect standard deviation. Part B, we're checking for that normality of the sampling distribution. So we're going to do n times p, which is going to be our sample size of 1,785, times p, which is 0.4. And then we also need to do n times 1 minus p, so 1,785 times 1 minus 0.4, which is 0.6. Make sure both of those values are at least 10. So 1,785 times 0.4 is going to give me 714. 1,785 times 0.6 will give me 1071. So because these are both greater than or equal to 10, my sampling distribution is approximately normal. Which again ultimately tells me that I can use z-scores. So here I'm going to use this mean and standard deviation in a z-score to find the probability that at least 44% of the people in the sample attended church. This is my x value, or really my p-hat value. So I have 44% minus the mean of 0.4 divided by the standard deviation of 0.0116. Again, when you do this calculation, make sure you do your numerator all together to keep those order of operations straight. And this gives me a z of 3.45. And then at least 44%, this really means 44% or more. So I want the area to the right of that z-score. So if I'm going to use table A, I would look up 3.4 where it intersects with 0.05. And that value is going to be 0.9997. But again, that's this region down here. So I have to do 1 minus 0.9997 to get my, my final answer, which is going to be about 3%, or 0.03%, I should say, 0.0003. If you use Staplet, you would do your mean of 0, standard deviation of 1, and then you would pick right tail for that top end, and then you would use your z-score of 3.45 to get 0.03%. So in this particular case, this would be surprising. 0.03% is pretty unusual, which would give us evidence that the newspaper's claim was incorrect. So we'll say yes, because 44% is unusual if 40% is actually true. And so this part D here is really just a lead in to the inference procedures that we'll be doing in a couple of weeks. But again, just looking at those probabilities, and if they're very small, typically less than 5%, then that gives us evidence to doubt a claim. So for your assignment, you guys just have one problem on page 283. Give that problem a shot, and if there was anything from the notes that you have questions about or anything in that problem, we can start with that in class tomorrow.